Yeah, so what I'd like to talk about today is a project I've been working on and off for a number of years called SNAPS, which is to do with trying to use predicted chemical shifts to kind of speed up or simplify the process of assigning the backbone of proteins. And I became interested in this through my work as an experimental officer, because part of my job, well, I noticed that there were a lot of people, structural biologists, working in York who didn't use NMR, but I thought that the projects probably could benefit from it. So I was kind of interested in what barriers there were to getting them to start using NMR. And for me, I think backbone assignment is kind of a bit of a bottleneck, because without a backbone assignment, you can get some kind of global data on like protein folding status, or see that there's some interaction happening. But the amount of information you can get with a backbone assignment is just so much more detailed and incredible. But the process of getting a backbone assignment, if you're trying to sort of sell it to someone, it's like, oh, well, you need to make an isotope labeled protein. Maybe you haven't done that before. You need to learn these different experiments, this theory, this software, and it's going to take you weeks, probably longer the first time. It's a bit of a hard sell. What I really wanted to do is to try and see if there was anything we could do to sort of simplify this process, either so that we can get new people doing backbone assignment and doing all the more detailed NMR, or at least if you're kind of helping and collaborating with another group so that you can kind of do their backbone assignments more quickly. And I think, yeah, if we could do this to bring more people into NMR, it would be really great for the field as a whole. Another thing that I was interested in is whether using predicted shifts, as well as speeding this up, is whether there was any way it could apply doing assignments to systems that are kind of difficult to use using a sort of standard backbone assignment workflow. So I'm not going to talk very much about generating the actual chemical shifts. I've kind of treated that as a bit of a black box. I'm just going to make note that there's a number of different tools that are available for this. For this project, I've mostly used ShiftX2. But my program that I've been developing, it doesn't really care where the chemical shift predictions come from. And so the way this works is basically you just feed in a PDB file of your structure, which can be experimental or from a prediction method. AlphaFold structures should work just as well. And it will just spit out a list of chemical shifts for each of the atoms. So basically, I think having the structures used to be a bit of a bottleneck itself, but now in the sort of AlphaFold era, you can generate predicted shifts pretty much any structured protein. Obviously, the predicted shifts have some degree of error with them. You're not going to get spot on. And so I was investigating this for ShiftX2, and one of the reasons I use ShiftX2 compared to the other tools is that when they published the paper on it, they provided a set of proteins which were excluded from the training process, and so I could use those for validating the method, and that was really, really handy. Definitely encourage people to do that if you can. So yeah, just looking at the distribution of the predicted shift on these 54 proteins in the validation set, you can see they're not perfectly Gaussian, but they're good enough that you can model the errors as normally distributed. To kind of obviously the errors here on these graphs are just in ppm, but it's more useful to express it as a fraction of the overall chemical shift range for the nuclei. And so to normalize that, I've just taken the central 95% of the distribution of chemical shifts that I got off BMRB. So that's what I am showing down here. And what you can see is that perhaps not particularly surprisingly, the C alpha and C beta chemical shifts are predicted most accurately as a proportion of the overall range. I guess just due to like well-known effects of secondary structure shifts. Whereas the others, it's a bit more variable. Are these accurate enough to use for, doing an assignment? So just as a kind of starting point, you could think about doing the most naive assignment method where you have like your predicted chemical shifts and you have a set of observed chemical shifts, and you just rank each, well, for each observed shift, you see how far each prediction is away from it, and then just rank them. So you have this predicted peak is closest, or this we're kind of using all of the chemical shifts on a residue. So you have a predicted residue with, say, amide proton nitrogen and the I and I-1 carbons, and you have the observed chemical shifts for each NMR residue or spin system, and we're just seeing which is the closest, second closest, and so on. And if you use, so it's covered up by this label, but on this top graph is if you're just using the kind of HSQC, just using the proton and nitrogen chemical shifts, and what you find is that the correct prediction is not very high in the rankings. The predictions are just not accurate enough. There's too many other peaks that end up falling closer by chance. And yeah, so assigning from an HSQC alone and predict shifts is not going to work. However, if you then include all of the carbon shifts, you're kind of, I guess you're dispersing the peaks a lot more. And so there's fewer kind of chance overlaps. And with this, you find that actually the prediction is closest to the observed peaks about 75% of the time, which is really promising. We can do better than this though. One thing I would just note at this point is that how you evaluate the accuracy of the chemical shift predictions for an application like trying to do an assignment is not necessarily the same as when the chemical shift predictor was being trained. Like if you're trying to get the overall match to be as good as possible, it might be a slightly different criterion to if you're trying to use these to do something else. I kind of think this is because it's sort of similar to like, I guess the well-known example of where you're trying to detect a rare disease, and like you might get an overall more accurate test, but that has like, say, more false positives or negatives. You might be more interested in false positives or more false negatives, if you see what I mean. So it's worth just bearing in mind when you're using chemical shift predictions that they might not be optimized for exactly what you want to do. Before I go into the actual program, I just thought I'd just say what my aims are for SNAPS. So I know there are already like a number of programs for doing automated assignment that will take you like right the way through the process. And I didn't want to just replicate what they were doing. Also, I'm just one person working on this in the time around helping with other projects and maintaining the facility. So I need to focus more narrowly just on the step of starting off with your peaks already picked and grouped into NMR residues or spin systems or whatever, and then using the predicted shifts to assign them to the sequence. Obviously, I would like it to be as accurate as possible. That's great, but also importantly is having some measurement of, for each specific assignment of the observed shifts to a residue, it would be really helpful to know, am I confident in that one, or is it possibly a bit less certain? I also wanted it to be resilient to missing data as much as possible, because, well, the validation set that I'm working with is fairly complete, but we all know real data is never usually quite as cooperative. And especially I think if you're working with people who haven't used NMR or are working more difficult systems, it would not be very helpful if it falls over. You're sort of missing 10% of your shifts or something like that. and I wanted it to fit into current workflows as much as possible. And also, I think for a tool like this to be used, it needs to be but easily accessible. So I want it to be eventually accessible via a simple web server, and hopefully eventually a CCPN plugin once I have learned how to do that. So this is just an overview of how the program works. You start off with your peak lists you've got from your spectra. You have a protein structure, either from X-ray or AlphaFold. And from these, you get your list of observed shifts on your kind of unassigned NMR residues. And you have a list of predicted shifts. And from before, we know roughly what kind of errors we expect in the predictions. So we can use that sort of model of the errors to construct a probability matrix, which just summarizes for each observed set of chemical shifts, how likely is it that you would get each set of predicted chemical shifts from that. I'll have a simple example of this on the next slide. And then once you have this probability matrix, you essentially want to find the assignment that is maximizes the probability of the predicted chemical shifts and observed chemical shifts. And that will generate a proposed assignment. At that point, you can either sort of output some plots and peak lists and sort of manually verify it, or you could think about looping back at this step, sort of assessing the assignment, saying, okay, these bits don't look right, try again with these extra constraints. Constructing the probability matrix is the hard bit in a way. Once you have it, there's a number of very fast algorithms for finding the best assignment, as long as you're treating it as a linear problem where the overall goodness of the assignment is just a sum of terms in this probability matrix. So it's actually, I use the log probability so that you can just sum them to get the overall sort of score for the assignment. So yeah, just a simple example to make it concrete, you might have these observed peaks in your HSQC. So each of them has a observed chemical shift of proton and nitrogen. You also have these predicted peaks. So each of them with a predicted proton and nitrogen. And say this is residue 1, residue 2, residue 3. That naive method I mentioned at the start would just assign X1 to A, probably correctly. But X2 is slightly closer to B than to C, so it would get that one wrong. The probability matrix would look something like this, with A1 having a higher probability, and then you've got these sort of intermediate probability ones for A, B, and C. Or sorry, B and C to 2 and 3. And the Hungarian algorithm for doing the assignment will just quickly see that, okay, A1, easy match. B2, that's an okay match, but then the global assignment will be less good. So the correct assignment here is A, A1, C2, B3. So the SNAPS assignment program, it doesn't actually, it's looking for the match between predicted shifts and observed shifts. It doesn't take into account it doesn't try and force adjacent residues to be consistent. And that's actually by design. We're not using the information about the sequential links so that if we have that information, we can use it as a sort of validation to see whether the assignment is correct. The output of the program is there's a sort of strip plot where you can kind of see very quickly regions where there's mismatches. Also, like, it will give a bar chart of where the mismatches are, and it will give a assignment confidence predictions based on whether it has sequential links. And I think, so in this case, it's got fairly large sections of it correct. It's made some errors, and these aren't errors that I think a human would make. You can see very clearly that, oops, sorry, there's massive mismatches here, but it's, at least I think of it as an advantage that it has failed in an obvious way rather than in a way which is hard to dissect. So looking at the accuracy on the test set of proteins, I should have mentioned the test set is skewed a bit towards smaller proteins, but there are some larger proteins up to sort of 400 or 500 residues, I think, were the maximum in there. So the overall accuracy was 88%, so certainly better than a naive method. But then if you break that down into which ones are high confidence, so that where there's multiple sequential links and no mismatches, you find that this set, actually the accuracy is like really good. It's 99%. So you have some assignments at least, which you can be really pretty confident in. Where you don't have quite as many sequential links, the assignment is still pretty good. And then as you have fewer and fewer, then it makes more and more errors. But again, just these sequential links are only really used to estimate the confidence in the assignment. They're not used in making the assignment itself. It performs quite well with missing data. So here I've just removed a random select proportion of the residues. And I was surprised by this. Even when you remove like 50, 60, or 70% of the residues, it's still the accuracy on the remaining data remains quite high, above 80% on this test set. What you do lose is obviously you have fewer sequential links to assess whether the assignment is correct. So, so the red line here is the overall accuracy of the assignment, and the blue line here is the proportion of ones which it's highly confident in. So still useful, but maybe not as useful. Obviously, for larger proteins, your 3D experiments, you might start to lose more peaks in, or your carbon chemical shifts become harder to measure. And unfortunately, it's not quite as robust if you remove a proportion of the carbon chemical shifts. But it still sort of gradually degrades, I would say, rather than completely failing. I was also interested in whether this kind of method would work if you had a more limited set of data. For example, suppose you were using this on a protein which was not uniformly carbon labeled, for example. That would limit the number of types of experiments you could do. And I was kind of simulating that by excluding certain categories of shifts. So the carbonyl shifts don't make a huge contribution to the accuracy. The C betas more so, but you're still kind of at about 65% accuracy without including any C beta shifts. What I would really like is for you to be able to do this with just an HNCO and an HNCA, for example. Then you're not kind of relying on carbon couplings in your experiments. Unfortunately, it doesn't quite work well enough. So you've got quite a severe drop in accuracy. It's probably not going to be useful, even more so if you just have an HNCA. The SNAPS program is flexible enough that you can include other types of data though, like for example, amino acid type data from, for example, a HADAMAC or a specific amino acid labeling or unlabeling experiment. And so if you add that in to the HNCA, you regain some of the accuracy. It's kind of working okay. This is a point where I kind of say, well, hopefully it will get, as chemical shift predictions get better, then the accuracy of this program will also get better without me having to do anything. But what I did do is I simulated how accurate the chemical shifts would need to be to improve the accuracy. And so if we have our full set of amide, proton, nitrogen, and the full set of INI-1 carbons, to produce this plot, I just made some sort of fake chemical shift predictions by adding random noise to the observed chemical shifts. And with about 10% standard deviation compared to the range, overall chemical shift range, whereas SNAPS is at about 80% accuracy with 5%. If we get the errors down to 5%, then this suggests we'd get up to 95% prediction accuracy. And shift X2 is somewhere between 5 and 10% errors, and the accuracy we get with shift X2 predictions is in between. So this all makes sense. If you could get to below 5% error, then this predicts we do get almost the completely correct assignments. Just out of curiosity, how good would the predictions need to be that we could predict directly of an HSQC? Unfortunately, unrealistically accurate. You would need the error in the predictions to be only about 1% of the chemical shift range to get 90% accuracy. So fortunately, that's convenient that would be, that's probably not going to happen. Okay, so just briefly, ways that I'm hoping to improve the program in the future is to find a way to use that the information on sequential residues to kind of iterate the assignment. I think there's a number of ways you could do this. The thing that sort of puts me off them is that they're less applicable to cases with missing data. I think where you have missing residues or ambiguous residues, that sort of breaks the sequential assignment methods or makes them less complete, which I was really trying to get away from with this. It's quite easy with this to generate, work out what the second and third best assignment for each residue is. And I'm still trying to work out what the best way to kind of display and use that information is. So I'm working with Gary and with a master's student in Kent, Hannah Morris, on NEF compatibility, because to my shame, it's not that at the moment. I've made some progress on the web server as well. If you would like, you can check it out at this URL. But unfortunately, it's been a little while since I worked on that, and since then, changes in Python and some of the libraries have meant that it's not as reliable as it could be, which I guess just shows how important it is to continually maintain online tools for them to remain useful. And yes, my intention is also to do a sort of fuller validation with AlphaFold structures just to check that it works okay. And so, yeah, I'd like to thank the people who've worked on this project with me. So Gary and Hannah have been doing a lot of work on NEF and import, and also looking into some of the extensions of iteratively assigning. My old supervisor, Michael Plevin at York, was really helpful discussions. And Dan Burns, who was working at Stratified Medicine Scotland, was really helpful